In today's real-life Orgo, we'll learn what makes an organic dye and how different organic dyes bond to various substrates as we follow Dina, the organic dye, on her journey of self-discovery. A real-life Orgo presentation brought to you by Nicole Blaise, Valerie Pope, Susanna Pritchett-Monavon, and Megan Vernino for Chem 262 at Purdue University. Chapter 1. Dina the dye wonders why she's different. Hello there! I'm Dina the organic dye. As you can see, I'm not like most organic molecules, which are usually white or clear. I'm different. I just wish I knew why I was so different.
Oh, Dina, being different isn't so bad.
Who is that?
Well, I'm the narrator, of course. Listen, Dina, there are 4 main qualities that make you a dye instead of a regular organic molecule. First, you absorb light in the visible spectrum, meaning you absorb wavelengths between 400 and 700 nanometers.
But narrator, why do I absorb visible light, but my friends don't?
Well, that's a good question. Unlike other organic compounds, which transmit or reflect all visible light, the electrons in dyes, like you, have a lower energy excited state than those not in dyes, which results in your ability to absorb lower energy light, i.e. visible light, and appear different colors. The lower energy excited state can be attributed to the chromophores and conjugation.
A chroma what?
A chromophore. A chromophore is a region of a molecule that gives a compound its color. Examples of chromophores include azo, nitro, methine, and more. Dina, you have an azo chromophore.
But my friend Jim has the same chromophore, and he's not colored.
Well, Dina, remember, you're colored because of your chromophore and your conjugation. If a chromophore isn't placed in a conjugate system, it won't cause any color. Conjugated systems are necessary for dyes because it's the fact that the electrons are dispersed through the molecule, forming various resonance structures, and being passed back and forth from the different atoms and around the aromatic rings that allows them to be excited by low energy visible light.
Oh! So let me get this straight. I'm a dye because I absorb visible light. And I absorb visible light because I have a chromophore in a conjugated system which allows for resonance of my electrons?
Exactly.
Okay. But then I have one more question for you. Why is my friend Nellie here a different color? He obviously absorbs visible light because he's red, and he has a chromophore in a conjugated system. But he has the same chromophore as me, so why are we not the same color?
Well, you see, chromophores do not correspond to one specific color. This is because a molecule's color is due to multiple factors, including the chromophore, molecule length or size, and oxychromes.
Again with the big words!
Oxychromes are just helper functional groups. They generally donate extra electrons to the conjugated system, in contrast to chromophores, which are usually electron withdrawing groups. Oxychromes, such as hydroxyl and NH2, are able to shift the electrons and thus the wavelength of light that they accept. Plus, oxychromes are also used to adjust the solubility of the dye.
I get it. Nellie and I are different colors because we have different oxychromes. Gee, I've learned so much information about myself today. It's just so exciting I could die. Chapter 2. Dina finds her perfect substrate. Hello there again. You know, I I've just been so lonely lately. What good is a dye if it doesn't color anything? I could really use someone to bond with.
Well, you're in luck, Dina. Each kind of dye has a specific type of substrate or fiber that it's designed for. There are many different types of dyes, but the most common organic dye, making up 66% of all dyes, is the azo dye.
Well, what kind am I? An azo? How do you know?
Yes, Dina, you're an azo dye. It's because of your azo group, of course. An azo group, you'll remember, looks like this. And it's right there in your center.
Awesome. So tell me who my substrate is. Does he have cute electrons?
Whoa, slow down there, Dina. You might be an azo dye, but there's many different types of azo dyes, like disperse, acid, and reactive. Each one has a different substrate that it dyes best. You'll have to find out which one is your match. Here comes a substrate now.
Hi, I'm Connor the Cotton Fiber. Do you think you have what it takes to be my perfect dye?
Well, I guess. What kind of dye are you looking for?
Well, I'm very demanding. I need a dye that'll be hydrophilic for the coloring process because I love dye baths. But I also need a dye to be hydrophobic once we're attached because I'm not going to have you to run off on me every time I'm laundered. Do you think you can handle that?
I don't know. I think I'm a little too hydrophobic for such a demandingly soluble dye process.
That's what I thought. Most of you dyes just can't hang later.
Don't worry, Dina. As a cotton fiber, Connor was in a group of substrates known as cellulosic polymers. These substrates need direct dyes, vat dyes, or reactive dyes to fulfill their complicated hydrophilic needs. Here comes another substrate now. Maybe you'll have more luck.
Enchantée, mademoiselle. I am Sammy the Silk. Would you be able to dye me? I'm really looking for someone who can color my world.
I would like to. What qualities are you looking for in your perfect dye?
I prefer a dye with a bit of a negative charge. It's a great complement to my positive one. It really allows us to bond with one another.
Oh, well, Sammy, I don't think I really have an anionic charge. You might be a little too positive for me. I actually find it kind of repulsive.
Very well. I shall go.
Oh, narrator, when will I find my perfect substrate?
Don't be discouraged. Every dye has its substrate. Polyamides and proteins, like silk, wool, and leather, just aren't for you. Substrates like that carry a cationic charge, especially during the dyeing process. So they usually prefer acid dyes, which have a negative charge that they can form an ionic bond with.
Oh, woe is me. Everyone has a substrate but me. What substrate would want me? I'm pretty hydrophobic, so I only barely dissolve in water, and I don't have any strong anionic or cationic charges.
Wait, did you say hydrophobic? No way. We have so much in common. I'm hydrophobic too. Water, ugh, I just can't stand the stuff. We should be best friends.
Oh my gosh, really? This is amazing! We do seem to have some great chemistry.
Ah, yes. Dina, you're a dispersed dye. Dispersed blue 165 to be exact. Dispersed dyes are very hydrophobic. That's why they're called dispersed dyes, because they disperse in water rather than dissolving. You have an affinity for polyester, like Esther here, and other cellulose acetate substrates.
Oh gee, thanks so much for your help, narrator. Let's do a little recap. Direct dyes and reactive dyes like cellulosic polymers because they're able to be hydrophilic during the dyeing process but then become hydrophobic or form a strong enough bond with the substrate that they don't wash away easily. And acid dyes prefer polyamides and proteins because they can form ionic bonds, and dispersed dyes, like me, prefer polyester and cellulose acetate because they're both hydrophobic?
That's exactly right, Dina. Professor Wenthold would be proud.
Wow, this is great! I'm so excited to have a new best friend. I think I might die. The end.